We're going to start our tutorial on matching networks by talking about these series element calculations. And by series element calculations, what I mean is that if we have the load ZL, what we want to know is what reactive element we need to place in series with the load. Is that a capacitor? Is that an inductor? And what value of capacitor or inductor do we need? And then we also need to know how long of a T line do we need to insert between that reactive element and the load. And so that's what we'll be calculating when we do these series element calculations. So series elements, overall, what they need to be, what we're looking for is where on the Smith chart will the insertion of a series element cause an intersection of the operating circle and the R equals 1 circle on the Smith chart. So I'll just go over that in kind of in theory here, and then I like to explain it just using an example. I think it makes the most sense. But the procedure step by step is that we just locate normalized load impedance on the Smith chart. So in one, you just take capital ZL, you divide it by the characteristic impedance of the transmission line that you're connecting with, this Z0 that you're connecting with, and that gives you ZL, and you just plot it on the Smith chart. So I'm just showing, for example, here is a ZL that I've plotted on the Smith chart. It looks like it's 0.25 plus J.5, something like that. What we then do is we draw our operating circle. Remember, that's constant reflection coefficient is what that operating circle represents. I'm showing it here in blue. You'll draw that by using your protractor. You'll put the point of the protractor at the center of the Smith chart and just draw that operating circle there. Then what you're going to do is you're going to rotate around the operating circle, and you're going to find the point where the operating circle intersects with the R equals 1 circle. So we're looking for, we've got these real circles along the Smith chart. We're looking for this one that I've indicated in dark black, which is R equals 1. And we notice that the operating circle intersects the R equals 1 circle in 2 spots. In this case, at R equals 1 and X equals J2, and down here at R equals 1 and X equals minus J2. We can cancel out the effects of the reactance by inserting a reactive element that is the opposite value of whatever intersecting point we have. So in this case, if we inserted a capacitor that had J2 of reactance, it would cancel out this J2 of inductance here. And in this case, we have minus J2, which is 2 ohms of capacitive reactance. If we inserted a series inductor, that would cancel this capacitance out. The last thing we have to do is calculate this transmission line length, and that is done by just looking at wavelengths towards the generator. We see where it intersects with wavelengths towards the generator. And this is for our load, and this is for one of the intersecting points with the R equals 1 operating, or the R equals 1 circle in the operating circle. So we look at those wavelengths towards the generator, and the length of the transmission line that we need to insert at comes from this number minus this number right here. So those are the steps that we go through. I like to do a numerical example. So we need to construct a matching network by inserting the appropriate reactive element at the appropriate distance into a 50 ohm T line terminated in an 11 plus J25 ohm load. So the first thing that we need to do is we need to calculate the normalized load impedance on the Smith chart. And remember, we just take the load impedance and we divide it by the characteristic impedance of the T line. So in this case, that's going to be 11 plus J25. And we need to divide that by the characteristic impedance of the T line, 50 ohms. And that gives us a normalized load impedance of 0.22 plus J 0.5. After calculating the normalized load impedance, which in this case was 0.22 plus J.5, we need to plot that normalized load point on the Smith chart. So I've brought up a Smith chart here, and you'll see that I've plotted the normalized load point. Here is the 0.2 circle right here, so I'm at about 0.22, and then you can see here I'm at the J plus 5 point. So the intersection of those two circles is the location of the normalized load impedance. After plotting the normalized load impedance, we plot the operating circle. To do that, we just placed our compass at the center of the Smith chart. We placed our pencil at the normalized load impedance point, and then we just drew a circle centered at the origin. The second step for determining the series matching element is that we need to find out where this operating circle intersects this r equals 1 circle, and I've marked those here and here. We see that that point is 1 plus J2, and that point right there is 1 minus J2. We can work with either of these points. Both of them will result in an appropriate matching network. For this example, I'm just going to continue on with 1 plus J2. After we draw the operating circle and find where it intersects with the r equals 1 circle, what we need to do is we need to draw two lines, both extending from the center of the Smith chart, one going through the normalized load impedance point, and then the other going through the intersection of the operating circle and the r equals 1 circle. Both of those lines need to extend out past the perimeter of the Smith chart. So I've drawn these two lines now for you. The first line that I drew here is for the point 1 plus J2, and what we'll see is that we come up here and we look at the wavelengths towards the generator scale, and we see that it intersects at wavelengths towards the generator at 0.188 lambda. For the line that extends from the center of the Smith chart out here, we'll see that it intersects with 0.76 lambda. And those are both on the wavelength to the generator scale. What we need to do is we'll find the length of transmission line by subtracting, that's 0.076. We'll subtract this number from this number to get the length of the transmission line. So that's 0.188 lambda minus 0.076 lambda, and that gives us a value of 0.112 lambda. So if we insert a capacitor of minus J2 at a distance from the load of 0.112 lambda, we would cancel out the normalized inductance here. This value, however, is normalized to the characteristic impedance of the transmission line, so what we need to do is we need to unnormalize it. We find that Z sub C is just going to be equal to Z0 times minus J2, and so we get that's 50 times minus J2, that's minus J100. So what we're saying from this analysis is that if we've got our load here, and in this problem the load was an 11 plus J25, so we've got 11 ohms, and plus J25 is an inductor. If we take some T-line and then we insert a series capacitor, and the series capacitor is 100 ohms, and the length of this T-line is equal to 0.112 lambda, so 0.112 wavelengths long, that's the electrical length of the T-line, then we will have created a matching network where the input impedance of this circuit is equal to the characteristic impedance of this circuit here. So that's a demonstration of series matching elements.